Hi, my name's Shan Fazal. I'm currently studying first year civil engineering at RMIT, and this is my structural analysis video project. In the following video task, I'm going to analyze the frame of the wardrobe, situated in Wheelers Hill, more specifically 54 Grandview Road. The structure is made of wood and falls under category 2, frame-like structures, specifically one of a portal frame nature. It consists of 3 slim rectangular pieces and boasts a symmetrical framing as rectangular objects would. The load type assigned to me in this analysis is a point load of 2.66 kilonewtons. This was assigned in order to allow for further calculations in shear force and bending moment, and hence allowing for further analysis of the structure. Other calculations, such as maximum deflection, the maximum slope, maximum shear stress, maximum principal stress, maximum bending stress, failure planes, and in-plane shear stress are also added to allow for an in-depth analysis of the particular structure. Rounding among other systematic errors may slightly vary results. Here is a picture of the wardrobe. To begin the analysis, I was first told to find the center of gravity, which indicated at which point all the loading was being transferred. With the origin at the bottom left of the structure, the coordinates for the center of gravity for my structure was 0.95 meters, the x-coordinate, and 2.03 meters being the y-coordinate. After this, I attempted to calculate the moment and the loading on each beam. However, due to the structure being statically indeterminate, I was forced to compromise. To attack this question, we had to assume that the top beams had a pin support, therefore making it statically determinate. Now, using equilibrium equations, forces and moments across the whole structure was found. And with those values, a shear force diagram was constructed, which illustrated the shear forces acting on the beam, this being 2.53 kilonewtons on the ends of the beam to counteract the 2.66 kilonewton universal load. A crucial part of the analysis was to construct a bending moment diagram, and that was calculated by calculating the isolated parts of the beam and calculating the moments in the middle of the beams. In this specific case, the moments on the ends of the beam were actually calculated to be 0 kilonewton meters, whereas in the middle of the beam, being 0.95 meters, it was calculated to be 1.2 kilonewton meters. Thus meaning that in the middle of the beam had a tendency of bending at a force of 1.2 kilonewton meters. For further analysis, we were challenged to find the moment equation, then to integrate that moment equation to therefore find the slope equation, and then double integrate that slope equation to find the deflection equation. The constants in these equations were found through substitution. Now that these equations have been found, it was now crucial for me to calculate the moment of inertia of my structure. Sri recommended me calculate the moment of inertia for only the top segment of my building. This is due to the calculation of the side members' moment of inertia being redundant. So using the moment of inertia equation of 1 over 12 times base times height cubed, I found my moment of inertia to be 158,333 meters to the power of 4. I then moved on to calculating the maximum deflection. This was done by letting the slope equal 0 and substituting it into the slope equation. The maximum deflection was found to be at x is equal to 0.548 meters. Now to find the maximum deflection value, we substituted that value into the deflection equation. And through doing this, we found the value to be negative 7.377 times 10 to the negative 14. And that, of course, being in meters. And this satisfies the deflection rules. The maximum slope was found by allowing the moment equation to equal 0. With reference to the BMD diagram, of course being the bending moment diagram, we can find that the moment is 0 at the ends, being 0 and 1.9 meters. We then substituted these values into the slope equation, thus giving us values of negative 1.168 times 10 to the negative 11 degrees and negative 1.27 times 10 to the power of negative 11 degrees. Pardon me, negative 10, sorry. After this, we found the maximum bending stress, which could be found using the equation sigma equals negative moment xy over MOI, being moment of inertia. And using this equation, we found the value to be negative 1.89 times 10 to the power of negative 11 MPa, being megapascals. The maximum shear stress for the entire structure can be found and calculated through an equation which was introduced to us prior in our lecture. After subbing these values in, the maximum shear stress of the structure can be found to be 9.99 times 10 to the negative 8 newtons per meter squared, or 9.99 times 10 to the negative 13 MPa. This leaves us with calculating the maximum principal stresses using the maximum shear stress values and the sigma values from earlier in the calculations. With sigma x being negative 1.89 times 10 to the negative 11 MPa, sigma y being 0 MPa, and shear xy being 0 MPa. These values only occur at 0 and 90 degrees. However, we choose to disregard the 0 degrees as it is not possible and just side with the 90-degree option. Thank you for listening to my video project. I do recommend going through the whole thing again with reference to my actual document. If not, I hope you enjoyed it, and thank you so much for listening.